Welcome to the Deep Dive, where we extract the most important nuggets of knowledge from a stack of sources, giving you a shortcut to being truly well-informed. Today, we're diving deep into a fascinating challenge that's quietly reshaping our world. How to make sense of the colossal amount of video data generated by cameras every single second. I mean, think about it. A single, maybe 1 or 2 megapixel CCTV camera. Sounds pretty basic, right? But that one device turns out something like 7 to 12 gigabytes of data every single day.
Every day. And that's just one. Multiply that across cities, homes, autonomous vehicles.
Yeah, you're suddenly looking at this just massive data deluge. It completely overwhelms the traditional ways of processing things.
Absolutely.
The problem is this. Cameras are everywhere, obviously, but our ability to efficiently process and, crucially, understand what they're seeing, especially in real time, well, it's a huge bottleneck.
It really is. We're constantly making these trade-offs,
Yeah.
between image quality, the spatial resolution, and how quickly we can actually process that information, the temporal resolution. Often it just comes down to communication bandwidth limits.
But what if? What if there was a way to capture all the important visual stuff, but with significantly less raw data right from the start?
Now you're getting to the core idea.
That's where this really brilliant concept called compressive sensing, or CS, comes into play. It's a powerful signal processing idea, and it offers this really tantalizing solution. It suggests we can sample signals, especially sparse ones, with way fewer samples than the old rules, like the Shannon-Nyquist theorem said we needed.
Right, the Nyquist theorem was kind of the bedrock for so long, at least twice the highest frequency you had to sample.
Exactly. But CS gets around that. How does it do it? It cleverly exploits the inherent redundancy in real signals. Things like images and videos have a lot of repeated information or predictable patterns.
Yeah, think about a video feed. A lot of the background might stay the same frame after frame. CS basically says we don't need to record all of that identical information every single time.
So it allows for this really dramatic data compression, right at the point of capture. Less data means less bandwidth needed, less storage space, and theoretically faster processing, right?
Theoretically, yes. That was the promise.
However, and there's always a however, it seems, this really elegant solution brought up a new, pretty significant hurdle.
The classic solution creates a new problem scenario.
Yeah. So while these CS camera sensors, especially the newer all-CMOS ones, are fantastic at saving bandwidth during sampling, and they minimize storage needs, the traditional tools like signal processing algorithms and deep learning models, they still need the reconstructed, uncompressed data to actually do their jobs.
That's the catch. They're trained on and expect standard video frames. They don't know what to do with this compressed format directly.
And the critical point is, most of the techniques used to reconstruct that data, to uncompress it, they're computationally really expensive. Super time-consuming.
Which completely negates the real-time benefits CS was supposed to offer. You're back to waiting for the computer to crunch the numbers, to painstakingly uncompress the video before you can even start looking for a car or a person.
So our mission today is to explore some really groundbreaking research that proposes a novel way to just completely bypass this reconstruction bottleneck.
You jump right over it.
Exactly. We're going to uncover how scientists are now managing to achieve object detection and localization directly on the compressed video frames themselves. This massively reduces the computational load and, maybe surprisingly, offers some other benefits too.
It's fascinating stuff.
So this deep dive is going to reveal how this, well, seemingly magical feat is done, the tech behind it, its actual performance in the real world, and crucially, why this innovation matters for you. Let's jump into the source material.
It really is a classic example, isn't it? Technological progress creates these new challenges down the line. Compressive sensing, the potential was so clear for data acquisition efficiency, but then the existing analytical tools just weren't built for it. This research tackles that exact disconnect. It's about making the analysis pipeline work with the new way of capturing data.
Okay, let's really try and get our heads around the scale of this data problem first. You mentioned that single 1-2 megapixel CCTV camera, 7 to 12 gigabytes a day. Put that into perspective for us. What does that actually look like?
Well, think about streaming HD video online. That amount of data is enough to stream several hours worth every single day from one single, relatively low-resolution camera.
Okay.
And like you said, that's just one camera. Now imagine a medium-sized city. They might have thousands of these deployed for traffic monitoring, security, you name it. You're very quickly talking about petabytes of information being generated daily.
Petabytes, that's
That's
a
about
quadrillion bytes.
a quadrillion bytes. It's a truly staggering amount. And all of this data, it needs to be stored somewhere securely. It needs to be transmitted, often over networks that are already pretty congested. And then if we actually want to get any useful insights or take real-time action based on what the camera sees, it has to be meticulously analyzed.
It's just a monumental challenge. The infrastructure alone must be immense.
It is. Data management, storage, transmission, it's huge.
And the current standard way we try to analyze this flood of data,
Mm.
it usually involves processing each frame individually, right? One after the other.
That's the typical approach, yeah, this frame-by-frame processing. And it demands absolutely hefty computational resources, as the source material puts it.
What kind of strain does that put on systems in practice?
Oh, it's immense. You're talking about needing serious investments in high-end hardware, powerful GPUs, servers. These things consume significant amounts of energy, which has cost and environmental implications. And even with all that power, there are unavoidable time delays.
Because each frame is treated like a separate picture to analyze from scratch.
Pretty much. Each frame is treated as its own full-resolution image that needs to be completely scrutinized. Imagine like an assembly line where every single item, no matter how similar it is to the one before it, has to go through the exact same, really comprehensive inspection process.
It's thorough, sure, but incredibly slow and resource-heavy.
Exactly. It makes genuine real-time applications a constant struggle. You're always fighting against that processing time.
So for us, the listeners, why does this actually matter? How does this computational strain affect things we might see or use?
Well, think about where cameras are absolutely critical. Smart cities trying to manage traffic flow in real time, maybe adjusting traffic lights based on congestion, security systems needing to detect an intruder instantly, or autonomous vehicles navigating really complex, busy streets.
Right, reaction time is everything there.
Absolutely. The more data these systems generate and try to process in the traditional way, frame by frame, the slower and more expensive those real-time responses become. Even a tiny delay in a self-driving car recognizing a pedestrian stepping out, or a security system identifying a potential threat, that can have really serious consequences.
And even for less critical things, like maybe advanced home surveillance.
Even there, the promise of getting an instant alert when a package is delivered, or if someone unexpected is at your door, that can be undermined by these bottlenecks. You might get the notification minutes late, or maybe even miss the event entirely if the system is overloaded. We keep hitting this wall where our ability to capture all this data is way ahead of our ability to process it efficiently enough for immediate use.
Okay, so this is where compressive sensing, CS, came in as this potential game changer. Before CS, our whole approach to sampling signals, like video, was basically dictated by the Shannon-Nyquist sampling theorem. That's fundamental in digital signal processing, right? What does it tell us?
Yeah, it's foundational. In simple terms, Shannon-Nyquist says that to perfectly reconstruct a signal without losing information, you have to sample it at a rate that's at least twice its highest frequency component.
Like needing a minimum number of photos per second to accurately capture a fast-moving object.
Exactly. Think of it that way. You need enough snapshots, closely spaced enough in time, to capture all the details of the movement or the change. If you sample too slowly, you lose information, you get aliasing, and the signal you reconstruct later won't be accurate. It's a fundamental limit that told us how much data we thought we absolutely needed to capture.
But CS found a way around this limit. You mentioned earlier it uses a trick involving inherent redundancy. Can you unpack that a bit? What does that redundancy mean, and how does CS use it to break the Nyquist barrier?
The trick is really recognizing that most real-world signals, especially images and videos, aren't just random noise. They have structure, they have patterns, repetitions, predictable elements.
Like the static background in that video feed example.
Precisely. Or the fact that objects tend to move smoothly, not teleport randomly. There's a lot of information that is either repetitive or can be reliably inferred from the context. The source uses the analogy of a verbose book. CS is like reading a good summary instead of every single word. You sample much less, but you do it in a very smart way that captures the essential information.
How does it know it's essential?
It relies on the concept that the signal has a sparse representation. That means, even though the signal looks complex, it can be simplified or represented using just a few key components or building blocks. Because CS knows the sparsity exists, it can be designed to capture just enough information to allow us to reconstruct those key components later, and thus reconstruct the full signal accurately. It's capturing the essence, the core information, not every single redundant pixel value or time step.
That makes sense. So by exploiting this inherent redundancy, CS allows sampling to happen at sub-Nyquist rates, meaning fewer samples than Shannon-Nyquist demanded, which radically cuts down the initial amount of data generated.
Yes, and the key advantage here is potentially massive, especially for systems that are choked by bandwidth limits. Think wireless transmission, or systems that need to operate with very limited storage or power, like sensors on a drone or in a remote location.
Right.
CS becomes extremely useful for capturing images and videos in those scenarios because the number of samples needed for the same video duration is much lower than that of generic imaging systems. And this allows for a critical improvement. You might be able to achieve higher spatial resolution, meaning a more detailed picture, without compromising temporal resolution, or how many frames per second you effectively capture. Or maybe keep the same resolution but drastically reduce the data rate.
So you could have a high-def, high-frame rate video feed, but the actual data stream coming out of the camera is much, much smaller.
That's the potential, making it feasible for situations where traditional cameras would just swamp the available bandwidth or storage capacity. Hashtag tag 1.3, the reconstruction roadblock.
Okay, so we've got these amazing CS cameras, like the newer all-CMOS sensor cameras, that can do this compressive sensing right in the hardware. They're genuinely saving a lot of bandwidth on sampling and reducing the memory required to store videos right from the get-go. It sounds like a huge win for efficient data capture. So,
Yeah.
what's the catch? Where did it go wrong?
Well, this is where that new bottleneck slams into view. Despite all those wins at the capture stage, the core problem for actually using the data remained. The traditional signal processing and deep learning models can realize operations only on the reconstructed data.
So the AI systems, the analytics, they still needed the old-fashioned uncompressed video frames.
Exactly. They were trained on conventional images and videos, and they fundamentally expect that kind of input format. They simply don't know how to interpret this new, highly compressed, differently structured data directly.
So the benefits of compression at the start are kind of wiped out later. Why is that reconstruction step such a problem? You mentioned it's computationally expensive.
It is. Hugely so. It's far from a simple unzip operation. Reconstructing those original high-fidelity frames from a compressed CS frame requires really sophisticated algorithms. One common approach, for instance, involves learning what's called an overcomplete dictionary.
An overcomplete dictionary, what's that?
Think of it as a massive library containing tiny image patches or patterns, way more patterns than you strictly need to represent any given image. The reconstruction algorithm then has to intelligently search through this huge library and pick out the right combination of patterns that, when put together, best explain the compressed data it received. It's trying to find the original signal that would have produced that specific compressed measurement.
So it's like trying to assemble a jigsaw puzzle with way too many pieces, and you only have a blurry photo of the final picture.
That's a pretty good analogy, actually. And algorithms like orthogonal matching pursuit, or OMP, are often used for this searching and assembly process. OMP is like that skilled detective trying to find the best combination of clues from the dictionary to recreate the original scene. It's iterative, it's complex, it's solving an inverse problem, figuring out the cause from the effect.
And that takes time and processing power.
A lot of time and processing power. The source gives an example. You could theoretically reconstruct a 100 frames per second video from a 5 FPS compressed video stream using a technique called pixel-wise coded exposure, but that reconstruction step itself becomes the agonizing bottleneck. It makes true real-time processing completely impossible in many cases. You gained efficiency at the camera, but you lost it all, and maybe more, waiting for the reconstruction.
Okay, so we have this big problem, amazing compression tech at the camera, but then this massive time-consuming reconstruction bottleneck before we can do anything useful like find objects. This brings us to what's really groundbreaking about the research we're diving into today. The authors claim they're the first to achieve object detection directly on these compressed frames, completely skipping that reconstruction step. I mean, that sounds almost like magic. How are they doing that? How can they see what's in the video without fully decoding it first?
It really is a fundamental shift in thinking. The traditional pipeline was, capture, compress, reconstruct, detect. These researchers are proposing capture, compress, direct detect.
Cutting out the middleman.
Exactly. Their core contribution, as they state it, is to propose a novel task of detection and localization of objects directly on the compressed frames. And they explicitly say this is for the first time in literature, which allows them to completely eliminate the need to reconstruct the original frames. Just that single change, skipping that step, has an immediate and massive impact.
And what is that immediate impact? What are the practical benefits of ditching reconstruction?
Well, the most obvious one is a drastic reduction in the computational load. By mitigating the need to reconstruct the frames, they effectively reduce the amount of data the detection algorithm needs to process. The paper mentions reducing the search rate up to 20 MET, which often corresponds to the compression rate they're using.
20 times less processing. That's huge.
It's a massive leap in efficiency. It directly opens the door to real-time applications that were simply out of reach before because of that reconstruction delay.
Okay, so how did they approach this? What was their strategy to make direct detection possible?
Their approach was really quite systematic, tackling it from multiple angles. First, they had to develop a robust compression framework. Essentially, they built a CS camera simulator. This was vital because they needed a way to generate the specific kind of pixel-wise coded exposure compressed video data required for their experiments, and crucially for training their AI models.
Right. They needed the right kind of hazy input data to work with.
Exactly. Second, they didn't just assume a brand new model was needed. They also explored and adapted existing traditional off-the-shelf detectors models normally used on uncompressed video to see how they performed or failed on this new type of compressed data. That gave them a baseline.
And the third step.
And most importantly, their third step was to propose a completely novel object detection framework specifically designed for compressed data. This wasn't just about tweaking an existing model. It was about architecting a new solution from the ground up, or significantly modifying one, tailoring it to understand the unique characteristics of these CS frames. It needed to learn to interpret information in a way no previous system had. Hashtag 2.2, how compression and labeling work for direct detection.
This sounds like it required some really clever thinking, not just about the AI model itself, but about how you even create these compressed frames effectively, and then, maybe even harder, how you teach an AI to understand them. Let's dig into that.
Absolutely. The foundation of their approach lies in how they generate these compressed frames. They use a technique called pixel-wise coded exposure, or PCE. Now, conventional cameras, as we know, have a global exposure time. Let's call it T. All the pixels in the sensor are exposed to light for that same duration, T, creating one distinct snapshot. Your frame rate is basically 1 divided by T.
Right, standard stuff. Each frame is a single static moment captured globally.
Exactly. But PCE cameras are radically different. Instead of one global exposure, each individual pixel on the sensor gets its own exposure pattern. Each pixel is exposed randomly for a specific fixed single-on fixed duration TB, which is actually longer than the conventional T would be. And this random individual exposure happens within a larger overall time window. Let's call it TV.
So pixels are turning on and off at different times within a longer window?
Precisely. And here's the crucial part. Only one image is read out at the end of TV. So instead of capturing, say, 13 separate distinct frames during that time TV, if TV was 13 times T, you get just one single consolidated unique image that represents everything that happened during TV.
Whoa. So if that total window TV is, say, 13 times longer than a normal frames exposure T, you're taking what would have been 13 individual snapshots and squashing all their information into one single compressed output frame.
That's exactly it. If TV equals C times T, you achieve a compression of C times, and your effective output frame rate drops to 1 TV. You're drastically reducing the number of frames the camera actually outputs.
How do they control which pixel turns on when? It can't be totally random, can it?
It's pseudorandom, controlled by what they call a sensing matrix, SMANAT. Here, M and N are the image dimensions, width and height, and T represents the compression rate, TCR, like our C or 13 in the example. This matrix is essentially a big coded instruction sheet for the camera sensor.
Like a blueprint for the exposure.
Kind of. Imagine it like a random pattern generator, but mathematically defined. It tells each pixel exactly when, within that total time TV, it should be active, exposed, value 1, or inactive, not exposed, value 1. The position of these ones, the exposure times for each pixel, is typically decided based on something like a Gaussian normal distribution, ensuring a good, random but structured sampling across space and time. This randomness is key to how it efficiently captures the information needed for reconstruction, or in this case, direct detection.
Okay, so you have this incredibly complex choreography happening at the pixel level, all controlled by this sensing matrix. What's the final result? What does the image that the AI sees actually look like?
The final acquired image, the coded image, IEM-EN, is essentially a summation. Each pixel's value is the sum of all the light it captured during those specific moments it was turned on, value 1 in the sensing matrix, within the total time window TV. Visually, the result is a single, quite hazy-looking image.
Hazy, like motion blur.
It looks a bit like motion blur, but it's much more structured than that.
Okay.
It's not just a simple smearing. It's a dense, information-rich representation that effectively encodes both the spatial information and the temporal information, the motion from all those multiple original frames into one single consolidated image. It's like a time-lapse photo where moving objects leave traces, but those traces are mathematically defined by the sensing matrix, allowing the AI to potentially decode the motion signature.
Right. That brings up the next massive challenge. If the input image is deliberately hazy, and the source even says manual labeling of the CS frames is difficult as the edges of moving objects are often indeterminable even to the human eye, how on earth do you train an AI to find objects in it? If we can't reliably draw a box around a moving car in that haze, how can we teach a machine to do it?
This was a really critical hurdle, yeah. And their solution, which they call enveloped boundary boxes, is a really clever piece of the puzzle. Traditional object labeling involves a human painstakingly drawing a tight bounding box around an object in each individual clear, uncompressed frame.
Which works fine when the object is sharp.
Exactly. But with these motion-encoded, hazy compressed frames, drawing a single, precise, static outline for an object that might have moved significantly during that single frame's capture window, it just doesn't make sense. Where would you even draw the line?
So how did they create these enveloped boxes? What's the process?
It's a smart, multi-step process that effectively bridges the gap between the clear, uncompressed world and this new, hazy, compressed domain. Here's how they did it. First, they took the original uncompressed video clips, the ones before they applied the PCE compression, and they meticulously manually labeled individual bounding boxes for every object of interest in every single one of those original constituent frames. They used standard, precise annotation tools like Vedic for this, so they had perfect, frame-by-frame ground truth information where the object was and how big it was in each clear snapshot.
Okay, so step one is perfect labels on the original easy-to-see frames.
Right. Then, for each block of, say, PCR, like 13 original frames that would eventually become one single compressed frame, they took all the individual bounding boxes for a specific object across that entire block of frames.
So if a car moved across the screen over those 13 frames, they'd gather all 13 slightly different boxes for that car.
Exactly. And then the final step, to create the single boundary box label for the compressed frame, they simply found the minimum and maximum X and Y coordinates that encompassed all of those 13 individual boxes for that specific object. This resulting single larger box effectively envelopes all the positions that object occupied during the entire compressed time window.
Ah, I see. It defines the entire spatial temporal footprint of the object within that single hazy frame. It captures the bounds of the smear.
Precisely. It accurately maps the hazy region corresponding to that object's presence and total movement during the capture period. It gives the AI a target area that represents the object's entire journey within that compressed frame. And importantly, they've made this labeled dataset openly available to the community, which is a fantastic contribution for future research.
So the AI isn't learning to find a perfect, crisp outline anymore. It's learning to recognize objects based on this motion signature embedded within the haze, guided by these larger, enveloping bounding boxes. That's a really unique way to teach an AI to see. It's learning a dynamic signature, not just a static shape.
Yeah.
Hashtag TechCheck 2.3, the related work, and why this is different.
Yeah, and it's important to kind of place this research in the broader landscape, differentiate it from other approaches people might be familiar with. A lot of work in video compression focuses on what's called advanced video coding, AVC methods. Think H.264, H.265, HEVC, the codecs used for streaming video online.
Right. Those work by making each individual frame smaller, using spatial compression like JPEG, and also looking for similarities between frames, right? Predicting motion.
Exactly. They primarily compress by reducing spatial redundancy within frames and temporal redundancy between consecutive frames. The model we're discussing today, however, performs compression along the temporal dimension in a fundamentally different way. It's collapsing multiple frames into one single representation.
So it's not just making frames smaller, it's reducing the number of frames dramatically.
Precisely. It's reducing the dimensionality of the data stream itself. This allows for direct detection on this tremendously reduced dimension, analyzing one information-packed, hazy image instead of a sequence of many, individually compressed but still distinct images. It's a different compression philosophy enabling a different detection strategy.
So the key distinction isn't just how they compress, but where the detection happens directly on this novel compressed format, before any reconstruction.
That's the core difference. Now, there has been other impressive work in the CS field focused on the reconstruction part. Some researchers have had success using deep learning to reconstruct high-quality original frames from CS measurements.
Recovering the clear picture from the haze.
Exactly. And that's valuable work for applications where you do need that full visual detail back. However, as the authors point out, that line of work, even using deep learning, takes a considerable amount of time, making it unsuitable for real-time processing. It still runs smack into that reconstruction bottleneck we keep talking about.
So this research is different because it avoids that reconstruction step altogether for the task of object detection.
Correct. They're not trying to improve reconstruction, they're bypassing the need for it for this specific downstream task, which makes their approach uniquely suited for time-critical applications where every millisecond counts. They're finding the objects without ever needing to see the perfectly clear picture first.
Okay, so they've got this innovative compression method using PCE, and a really clever way to label the resulting hazy data with enveloped boxes. Now let's get into the nuts and bolts. How do they actually build the AI model to handle this? And, maybe most importantly, how well did it actually work? What were the results? Hashtag tag 3.1, building the dataset for learning.
Right, building the right dataset is absolutely foundational for training any AI model. They started by using a subset of raw video clips from YouTube 8M, which is a massive public video dataset. But they were careful they specifically avoided artificially edited ones.
Why avoid edited videos?
Because editing, things like scene cuts, transitions, fades, special effects, they can disrupt the continuous motion of objects. An object might disappear in one frame and reappear somewhere else instantly due to a cut. This breaks the smooth temporal information that the PCE compression relies on and encodes. It would also make creating those continuous enveloped bounding boxes impossible or meaningless across an edit. They needed raw, unedited footage with natural motion.
That makes sense. And they couldn't rely on YouTube videos alone, right? To make sure the model works well in the real world, you need lots of variety.
Exactly. Generalizability is key. Relying on one source, even a huge one, can lead to the model learning biases specific to that source. So, to increase the variety and ensure the model was robust, they collected more videos on our own.
They went out and shot their own footage.
Seems like it, or sourced it carefully. The goal was to deliberately incorporate more motion and object variants than they might find in a typical data set. They captured scenes systematically, multiple days and during different parts of the day. They were really trying to cover almost all the scene dynamics you might encounter, different lighting conditions. Bright sun, dusk, varying levels of object movement, fast, slow, camera movement, panning, static, different backgrounds, everything.
So they built a bespoke dataset tailored for training on diverse, motion-rich, real-world scenarios to generate the best possible compressed training data.
That's the idea. This ensures the model learns the fundamental signatures of objects in compressed frames, rather than just memorizing what cars look like on sunny days in YouTube clips. These carefully selected clips were then processed through their compression framework using the PCE method and labeled using the enveloped boundary box technique we discussed.
Did they mention the specific compression settings they used for training?
They did. For the training data, the TCR was set to 13, meaning 13 original frames were compressed into one output frame, and TBU was set to 3, which relates to the individual pixel exposure duration within that longer window, influencing the nature of the haze. And critically, they noted that the random sensing matrix has been varied for each set of TCR number of frames.
Why vary this sensing matrix?
To ensure the model didn't just learn to decode one specific random pattern of compression. By changing the sensing matrix for different blocks of frames, they forced the model to generalize, to learn how to detect objects regardless of the specific pseudo-random way the compression was applied in that instance. It adds robustness.
Okay, so that's the training data. What about testing? How do they evaluate it?
For testing and validation, they turned to a standard, well-respected benchmark, the KITTI Multi-Object Tracking Dataset. This dataset is widely used for evaluating autonomous driving perception systems. They took the ground truth labels from KITTIA, which are precise boxes on original frames, and applied their enveloped bounding box generation method to create their compressed test data.
So they tested on a completely different data set than they trained on using the same compression and labeling process.
Exactly, which is standard practice to check for generalization. In the end, their final training dataset comprised a 180K samples. That's 180,000 compressed frames, each paired with its corresponding enveloped boundary box labels for the object classes cars and person. A pretty substantial and carefully constructed dataset for tackling this novel problem. Hashtag 3.2, the proposed model architecture and training.
All right, custom data set ready. What about the AI model itself? What kind of neural network architecture did they build or adapt to actually learn from these unique, hazy, motion-encoded frames?
So the input to their network is that single MN frame, which remember is temporally compressed from an original MKNXT video segment, a 2D image containing 3D temporal info. The output from their model is structured as MTA-NT-ACE5.
Okay, let's break that down. MT and NT. That means the output feature map is spatially smaller than the input image.
Yes, the spatial resolution is actually reduced by a factor of t in the output representation. Effectively, the model is summarizing the spatial information, but the critical part is the 5-foot. This represents the 5 key variables the model predicts for each location in that smaller grid, P, W, H, X, Y.
Right, so P is the probability that an object is even there.
Correct. The object presence probability or confidence score, and W and H are the predicted width and height of the enveloped bounding box.
And X and Y are the setter coordinates of that box, so it's predicting existence and the enveloping box parameters.
Exactly. And the paper notes that while the spatial resolution is reduced, the existence of the objects along the temporal dimension is preserved. The model learns to locate the object's temporal footprint within this spatially condensed, temporally encoded image.
Is this a completely new network architecture they designed from scratch? Or did they build on something existing?
They mention that our network is largely based on YOLO. YOLO, which stands for You Only Look Once, is a very well-known and highly influential real-time object detection model. It's famous for being fast and pretty accurate.
Okay, so they started with YOLO, but presumably they had to make some significant changes to make it work on these weird compressed frames.
Oh, absolutely. Standard YOLO wouldn't work well out of box here. They highlighted 3 major modifications they made to the original YOLO architecture to adapt it for this task.
What were those key changes?
First, they incorporated residual connections into the network structure. These are essentially shortcuts that allow information, particularly low-level features like edges or basic textures, to bypass several processing layers and feed directly into deeper layers.
Why is that important here?
It's crucial for preserving the low-level features. In these hazy, compressed images, those subtle details are easily lost as information passes through many layers. Residual connections act like an express lane, helping to carry that vital, fine-grained information deeper into the network without it getting washed out or degraded. This helps the model make sense of the less distinct input.
Makes sense. What else?
Second, they used ResNet blocks instead of YOLO's original, simpler vanilla convolutions. ResNet blocks, which are the core component of residual networks, are known for enabling the training of much deeper networks effectively. They also have this characteristic of preserving features well, and they're generally considered more robust for complex image processing tasks, especially when dealing with challenging or unusual input data like these CS frames. They are also shown to preserve the low-level features, reinforcing the first point.
Okay, so residual connections and ResNet blocks to better handle the hazy, feature-scarce input. That seems logical. What about the actual training process? How did they get this adapted network to learn?
In terms of training specifics, they reported that the network converges within 25 epochs. That's relatively quick, suggesting the architecture and training setup were quite efficient. They used the Atom Optimizer, which is a very common and effective algorithm for updating the network's weights during training with standard parameters, learning rate 1E5, etc.
And batch size, data split.
The mini batch size was 16, meaning the model processed 16 compressed frame samples at a time during each training step. And the data was split 7.3 for train and test. So 70% for training the model and 30% held back for testing its performance on unseen data.
And how did they measure error? What were the loss functions?
They used a combination. For the localization part, getting the bounding box, W, H, X, Y, right? They used mean squared error. This penalizes the model based on how far off its predicted box dimensions and center are from the true enveloped box. For the classification part, predicting the probability tuple of an object being present, they used multi-class cross-entropy loss, which is standard for classification tasks. This combination ensures the model learns both where the objects are, localization, and that they are present, detection, accurately within this compressed domain.
Okay, technically impressive setup. Custom data, adapted YOLO with ResNet blocks and residual connections, careful training. But the million-dollar question is, how well did it actually perform? How accurate was it at finding cars and people in these hazy frames? And, just as crucial for the real-time goal, how fast was it?
Right, performance metrics are key. They evaluated their model's accuracy using mean average precision, MAP. This is a standard and quite rigorous metric in the object detection field, and they followed the specific COSIO dataset method for calculating it.
What does that involve?
It means they calculate the average precision, AP, for each object class, car, person, across a range of IOU thresholds, from 0.50 up to 0.95. IOU stands for intersection over union. It measures how much the predicted bounding box overlaps with the true enveloped bounding box. Averaging the AP across these multiple strictness levels, IOU thresholds, gives you the MAP, providing a really comprehensive measure of accuracy, not just performance at one arbitrary overlap level.
Okay, so it's a tough, standard benchmark.
Yeah.
What was the final MAP score for their novel model?
The overall result was an accuracy of 46.27% AP.
46.27%. Okay, how does that break down for cars versus people?
It performs slightly differently for each class. The car class got an MAP of 42.42%, and the person class achieved 50.12%. So a bit better at detecting people than cars in this compressed domain, but respectable performance for both.
Now, for listeners used to seeing MAP scores on standard data sets, maybe 46% sounds, well, that's super high. Context must be really important here, right? We're talking about detection in intentionally degraded compressed data.
Context is absolutely everything here. You cannot directly compare this 46% to, say, 70% or 80% AP achieved by a state-of-the-art model running on crystal-clear, uncompressed video frames. It's a completely different, much harder task. And their comparative analysis, which they present in a table, really drives this home.
What did that comparison show?
It showed that their proposed model, achieving that 46.27% MAP with an inference time of just 28 milliseconds and a model size of about 242 megabytes, actually performs far better with that of the generic models that work on the original domain when those generic models are applied to the compressed data.
So if you take a standard object detector and just feed it these hazy images, it does much worse.
Much, much worse. In fact, the paper explicitly states that most of the state-of-art architectures fail to detect even the presence of an object in the compressed domain if they weren't specifically adapted or fine-tuned for the CS data. They simply aren't equipped to interpret this kind of input. This research fundamentally bridges that capability gap.
So what does this all mean for us, practically speaking? It means they haven't just made it possible to see objects in these compressed, hazy videos, which others couldn't do reliably, but they've done it in a way that's incredibly fast and efficient compared to alternatives. That sounds like a huge win for actually using this in the real world.
It absolutely is. The balance is key. When they compared their model specifically to other state-of-the-art object detection methods that were fine-tuned or designed for compressed data, their model really stood out for operational efficiency. Well, they mentioned one competitor, Sniper. It achieved a slightly higher MAP, about 2.9 percentage points higher, so marginally more accurate by that metric. However, Sniper was a much heavier architecture, consuming 536 middlebeat of memory, more than double their model size, and it took significantly longer for inference, 49.16 meters compared to their 28 meters.
Almost twice as slow.
Exactly. So in stark contrast, their proposed model only consumes 242 mbreaths and runs inference in just 28 meters. This makes their solution arguably the leader when you consider the practical trade-offs. That slightly lower MAP seems like a very reasonable price to pay for such dramatic gains in speed and reduced memory footprint, especially for real-time systems.
This does raise that interesting question again. How can a model be so effective when the input looks so obscured to us? It really suggests the model is learning something deeper, more abstract than just matching surface appearances.
I think that's exactly right. It's not just recognizing the pixel pattern of a car, it's learning to interpret the signature of a car-like object moving within that compressed, temporally encoded data stream, its overall shape, its motion profile captured in the haze, its general presence. The model isn't just confused by the haze, it's actively interpreting the information embedded within the haze.
And the researchers' conclusion.
Their conclusion is that their solution achieves the best balance between the accuracy, inference time, and memory constraints, and that specific balance, as they rightly point out, is absolutely critical for enabling real-time deployment, especially on devices out in the field, at the edge, where computational resources are often strictly limited.
Okay, the performance numbers look great, especially that balance of speed, accuracy, and efficiency. But let's talk about the real-world implications. How robust is this system? Does it work well under different conditions? And are there any unexpected consequences or benefits that emerge beyond just making detection faster? Hashtag 4.1, model generalizability and robustness.
Generalizability is always a huge question for real-world AI. Does it only work under the exact conditions it was trained on? The researchers specifically tested this by varying those key compression parameters we talked about earlier, the compression rates, TCR, and the bump times, TB, which control how the pixel-wise coded exposure works.
And what did they find? Did the accuracy plummet if they changed the compression settings?
Encouragingly, no. They looked at the accuracy, AP values at different IOU thresholds, for various combinations of bump times and compression rates. Their finding was that there was no conclusive proof of any trend of decline or ascent in the MAP with respect to the bump time or the compression, unless they are the extremes.
So unless you push the compression way too far or use really weird settings, the model is pretty stable. It's not overly sensitive to the exact haziness pattern.
That's what the results suggest. It's excellent news because it demonstrates that their model is generalized and can work with other compression rates and bump times. It seems capable of generalizing over the entire natural set of the compressed domain. The model didn't just memorize how to detect cars compressed at exactly TCR 13. It learned the underlying principles of how objects manifest in this unique, motion-encoded data format, regardless of the precise degree of compression, within reasonable bounds.
Why would it be so robust, given how different the input images could look depending on the motion and compression?
The researchers suggest the reason lies in the very nature of these CS frames. Because each frame inherently encodes motion over a period of time, the appearance of objects within that frame naturally has high variance. A car moving slowly will create a distinctly different Haze signature compared to the same car moving quickly.
So the training data itself is naturally diverse in terms of appearance due to the motion encoding.
Exactly. This inherent variability during training, constantly exposing the model to different motion signatures for the same object class, likely forces it to learn a more fundamental abstract representation. It learns to read the ghost or the motion trail of an object, if you will, rather than just memorizing one specific static appearance. It becomes robust because the input is so varied.
And they showed examples of this working in practice, right? I remember seeing figures in the source material.
Yes, they included illustrations, figure 3 in their paper, showing the model successfully detecting objects in really quite complex and dynamic scenarios. For instance, situations where both the object, like a car, and the camera were moving simultaneously, cases where the object was moving but the camera was stationary, and even the opposite, a stationary object seen by a moving camera.
It could handle multiple objects, too.
Yes, it successfully detected multiple objects within a single compressed frame in some examples. This really demonstrates that it's not just a theoretical concept or something that only works in controlled lab settings. It shows practical robustness in diverse dynamic conditions that mimic real-world environments, which is a significant achievement for deployment. And this generalizability is directly linked to practical deployability, which is arguably one of the most exciting outcomes here. The researchers didn't just simulate this, they actually deployed it. They explicitly state the model was also deployed on NVIDIA TX2 and inferred using TensorERT with a runtime of 34 meters with AMAP of 45.11, 0.025% loss from the original model.
Okay, unpack that for us. An NVIDIA TX2.
That's not a giant server, is it?
Yeah. TensorERT.
No, exactly. An NVIDIA TX2 is a relatively small, low-power embedded computing board. Think of it as a powerful brain for devices like drones, robots, smart cameras, or other edge devices that operate out in the field right where the data is being captured rather than in a data center. And Tensor is NVIDIA's software library specifically designed to optimize trained deep learning models for faster inference speed on NVIDIA hardware, especially these embedded platforms.
So the fact that they got it running at 34 milliseconds, which is nearly real time, about 30 frames per second with almost no drop in accuracy, 45.11%, AP versus 46.27% originally on this kind of low-power hardware. That's a big deal.
It's a huge deal. It signifies that this solution isn't just theoretically sound or only feasible on high-end, power-hungry servers. It genuinely works for real-time inference on an embedded board. This is absolutely crucial for countless real-world applications where deploying big, expensive GPUs isn't practical or cost-effective, or where you might not have a stable, high-bandwidth connection back to the cloud for processing.
Right, so you can put the intelligence right inside the camera or the drone itself.
Precisely. Connecting this to the bigger picture, getting this kind of performance on a device like the TX2 means the technology can be integrated directly into surveillance cameras, drones, smart factory robots, maybe even advanced driver assistance systems in cars, or sophisticated home security systems. It allows for decentralizing the AI.
Pushing the intelligence out to the edge. What are the benefits of that?
Several key benefits. First, you save enormous amounts of bandwidth because you're processing the data locally instead of sending massive raw or even traditionally compressed video streams up to the cloud. Second, you drastically reduce latency, the delay, because the analysis happens right there, enabling much faster reactions for critical real-time tasks. And third, it enhances local capabilities without relying on constant connectivity. It makes powerful AI feasible in many more places.
Okay, now this next point really caught my attention. It seems like a completely unexpected side effect, but potentially a very important one. The research highlights, and I quote, "We can observe that the compressed frame contains hazy information, due to which the privacy concerns raising due to surveillance can be mitigated." Yeah, wait a minute. So not only is this approach faster and more efficient for the AI, but the inherent haziness actually provides a kind of built-in privacy protection for humans. That's quite a twist, like having an AI watchdog that sees what it needs to see, but not everything in sharp detail.
It's a fascinating and incredibly valuable paradox, isn't it? We've established that the compressed frame is intentionally hazy, especially to the human eye. You can usually tell something is moving, you can often make out the general shape of a person or a car, but specific identifying features, faces, license plates, maybe text on clothing are often obscured or completely indistinguishable.
But the AI can still detect the person or car.
Exactly. Yet, as the paper notes, this hazy frame still preserves all the information intact required for the reconstruction of the frames, while simultaneously protecting privacy from casual observation. It's like having information locked in a safe. The core data is there, technically, within the compressed representation, but you can't just glance at the compressed frame itself and easily extract sensitive personal details. You'd need to perform that computationally intensive reconstruction process, which isn't happening in this direct detection pipeline.
So the AI model learns enough from the hazy structure and motion signature to robustly identify this is a car or this is a person, but a human looking at the same compressed data stream, or maybe someone intercepting it without the specialized reconstruction tools and keys, can't easily see compromising personal details. That could be huge for ethical AI, especially in public spaces.
It absolutely could be. It offers a potential way to get the utility of surveillance, like detecting dangerous situations or counting people for crowd management, without the same level of intrusive monitoring of individuals. The researchers argue this finding strongly suggests that their model has learned an essential latent representation of the objects in the compressed domain rather than to overfit onto the hazy information.
Meaning it's learning the deeper concept of carness or personness from the motion and shape cues, not just memorizing specific blurry pixel patterns.
Exactly. It's extracting the abstract features that signify the object category without needing all the fine-grained, potentially privacy-invasive details. This could be a real game changer for balancing the benefits of AI-powered monitoring with crucial ethical considerations about surveillance and data privacy. It opens a path towards more responsible deployment.
This almost sounds too good to be true, though. An AI seeing clearly through haze that obscures details for humans. It feels counterintuitive. Is there some deeper, maybe mathematical reason why this is even possible? Why doesn't the compression just destroy the information the AI needs?
There is actually a strong theoretical basis for this, and it connects back to some fundamental concepts in information theory, signal processing, and high-dimensional geometry. The researchers briefly mentioned the link between compressive sensing and a mathematical result called the Johnson-Lindenstrauss lemma.
Johnson-Lindenstrauss. Okay, what's the gist of that lemma? How does it relate to seeing through haze?
In essence, the Johnson-Lindenstrauss JL lemma is about the preservation of distances between the higher dimensional space to the lower dimensional spaces. That sounds abstract, I know.
Yeah, maybe simplify that a bit.
Okay, imagine you have a bunch of data points scattered in a very high-dimensional space. Think of each point representing a complex original video frame with millions of pixel values. Compressive sensing, in a way, squishes or projects these points down into a much lower dimensional space, our single, hazy, compressed frame. The JL lemma basically states that under certain conditions, related to the randomness of the projection, like our sensing matrix, the distances between pairs of points are surprisingly well preserved even after this drastic squishing.
So if two original video frames were very different, their compressed versions will still be relatively far apart. And if two original frames were similar, their compressed versions will be close together.
Roughly speaking, yes. The relative geometry, the structure defined by how far apart things are, is largely maintained, even though the absolute coordinates change and dimensions are lost. Think of it like taking a detailed 3D globe and projecting it onto a flat 2D map. You lose the third dimension, things get distorted, especially near the poles, but the relative distances and arrangement of continents and oceans on the map still reflect their relationships on the globe reasonably well.
Okay, so the AI isn't trying to reconstruct the full 3D globe, the original video. It's learning to read the important relationships, the distances between different types of landmarks directly on the compressed 2D map.
That's a great way to put it. The lemma provides the theoretical backing that the critical structural information needed for object identification. The features that distinguish a car signature from a person's signature or background noise is likely maintained in those preserved relative distances within the compressed domain. The convolutional neural network, being excellent at learning complex patterns and features from spatial data, is simply leveraging those preserved relationships on the 2D map of the compressed frame. It doesn't need the full 3D detail to figure out what's what.
So that helps explain why object detection in CS frames is possible using convolutional neural networks. It's not magic. There's solid mathematical theory suggesting the necessary information survives the compression, just in a different form.
Exactly. It offers a theoretical foundation that complements their strong empirical results. Hashtag tag 4.5, a glimpse into the future.
This research really does feel like it opens up a lot of exciting possibilities, going beyond just this specific paper. What do the authors themselves see as the future trajectory for this kind of technology?
They have a pretty clear vision. They conclude by envisaging that this work will be the beginning of object detection and other computer vision tasks in the CS domain. They see this as a starting point, a proof of concept.
So if object detection works directly on compressed data, maybe other more complex tasks could too.
That's the implication. Things like recognizing specific activities, like running, falling, fighting, tracking objects more precisely over time, even within the haze, maybe even detecting unusual anomalies or events directly in the compressed stream without ever needing full reconstruction. It could unlock a whole suite of vision tasks in this efficient, privacy-preserving domain.
And they specifically mention surveillance.
Yes, they predict a significant improvement in surveillance as it embraces privacy at its core. That dual benefit efficiency plus inherent privacy makes it incredibly compelling for applications where monitoring is needed, but intrusiveness is a major concern.
So, for you, the listener, this research isn't just some obscure technical paper about algorithms. It really opens doors for countless applications across many industries. Anywhere bandwidth is tight, or computational power on the device is limited, or, maybe increasingly importantly, where privacy is a significant concern. This approach offers a new path forward.
Think about smarter city infrastructure, more efficient industrial automation, safer autonomous systems, even more responsive and less intrusive personal smart devices in our homes. This could make advanced AI vision far more accessible, less resource-hungry, and, as we've discussed, inherently more aligned with ethical considerations around data privacy.
It genuinely feels like it could redefine what's possible right at the edge of our networks, pushing powerful AI closer to the source of the data, making insights faster, cheaper, and potentially more responsible.
I agree. It's a really promising direction. Hashtag tag outro.
And that brings us to the end of another deep dive. Today, we started with that overwhelming problem, the sheer volume of video data pouring from cameras everywhere. We talked about how just one simple CCTV camera can generate gigabytes daily, and how processing this frame by frame swamps traditional computing resources.
The data deluge is real.
We then explored the elegant concept of compressive sensing, a clever way to capture the essential information with far fewer samples by exploiting redundancy. But we immediately ran into that frustrating reconstruction bottleneck. Even with efficient capture, traditional AI needed the original uncompressed frames, and getting them back was slow and expensive, often killing the real-time dream.
The efficiency gain was lost in translation, essentially.
Exactly. But then we unveiled the truly ingenious solution presented in this research, performing object detection and localization directly on those compressed, hazy video frames, completely bypassing reconstruction.
We saw how techniques like pixel-wise coded exposure create these unique motion-encoded frames, and how enveloped bounding boxes provide the necessary labels for the AI to learn from this strange new data format.
And the results were striking. An incredible potential for up to 20x reduction in the processing needed compared to analyzing reconstructed frames. Genuine real-time performance demonstrated on low-power embedded hardware like the NVIDIA TX2 with very little loss in accuracy.
And significantly better performance than standard detectors when applied to this compressed data, plus a great balance of accuracy, speed, and model size compared to other specialized methods.
And maybe the most surprising and potentially impactful benefit, that inherent privacy enhancement. The data is structured in a way that's clear enough for the AI to perform its task robustly, but remains hazy and less revealing to casual human observation.
A potential win-win for utility and ethics.
Absolutely. So this isn't just a minor technical tweak. It suggests a fundamental shift in how we might interact with cameras and AI in the future. It makes advanced vision tasks potentially more accessible, much more efficient, and perhaps significantly more ethical across a whole range of applications, from public safety and smart cities to robotics and even our personal devices. It avoids processing every single pixel of every single frame, yet still extracts meaningful insights. So as we wrap up today's dive, here's a final provocative thought for you to chew on. If compressive sensing can enable robust AI perception while inherently enhancing privacy by making the raw data hazy to humans but interpretable by AI, what other domains currently reliant on high-resolution data could benefit from a similar compressed domain strategy? Could we analyze medical scans, satellite imagery, or financial data more efficiently and perhaps more securely by teaching AI to work directly on cleverly compressed representations? Could this paradigm shift fundamentally change our relationship with information, surveillance, and data processing, ushering in a new era of what we might call intelligent efficiency, with privacy and ethics baked in from the start? Something to think about. We'll see you next time on The Deep Dive.